Okay, so first thing, that problem we were doing in class last time, number 2 on the first set of entropy problems. The thing that we were missing there um, is you need to recognize, well, the full solution is posted on, I just put it, I just updated the solutions to the first set of entropy problems to include that one now. So you can see the whole solution, but um, so entropy 1, number 2. Here's the basic idea that we were missing is the definition of change in entropy is the integral from state 1 to state 2 of dq over temperature at the boundary for an internally reversible cycle. Okay. And we were dealing with a Carnot cycle, so that is internally reversible. And so the Carnot cycle is internally reversible. And so for the two adiabatic processes, so you can think of the change in entropy as being equal to this for our Carnot cycle that we're dealing with in the problem. And so that means that for the two adiabatic processes, since there's adiabatic means there's no heat transfer, there's no change in entropy. The entropy is constant over those two adiabatic processes. So the change in entropy for the isothermal compression plus the change in entropy for the isothermal expansion has to equal 0 because it's a cycle, and those are the only two where you have changes in entropy. Okay, so I don't know what you remember about this problem, but so we were looking at two processes in this Carnot cycle. One was isothermal compression, and in that one we were given all this information. We were given temperature and the beginning and ending pressure. For the isothermal expansion, we weren't given the pressures. So if you start out with the isothermal compression, you can calculate a bunch of stuff, the stuff they ask for, and you can calculate the change in entropy. Then that tells you what the change in entropy is for the expansion, and then you can get everything from there. But the solution's posted online. Anybody have any homework questions? Yes. Okay. Okay, so entropy 2 number 2. We have an isolated system. So what's that going to mean for us? if you have an isolated system, then what? Yeah, so right, so there's no material transfer, no heat transfer, no work done. But the way that's probably going to come up is we know that in an isolated system, uh, there can only be positive change in entropy. Um, so it's an aluminum container, aluminum vessel with a mass of 0.1 kilograms and a 0.2 kilogram piece of steel, um, and 10 kilograms of liquid water. Um, the vessel has an initial temperature of 20 degrees Celsius. Steel has an initial temperature of 150 degrees Celsius. And the water has an initial temperature of 5 degrees Celsius. Um, and we want to know first, what's the equilibrium temperature? Second, what's the entropy produced? Um, and then last, show that the reverse process couldn't happen in an isolated system. Okay, so we did an example that was a lot like this, but ours just had two things instead of three. Um, this is two solids and one liquid. We're going to assume that they're all incompressible. So each material is incompressible. And so that says, so for incompressible materials, you just have one specific heat you deal with. So C is equal to du temperature. That's only for incompressible materials. And so du is equal to C dt. And so the change in internal energy is equal to C times the change in temperature. Well, now we have to know the specific heats for each of these three materials. For water, liquid water, in SI units, it's 4186. For steel, I don't know what that is. I don't know what it is for aluminum. But those are just things you can Google. And so um, since this system is isolated, there's not going to be any total change in internal energy for the system. And so uh, the change in internal energy is going to be zero. And that's going to be the mass of the water times the change in internal energy of the water plus the mass of the steel times the change in internal energy of the steel plus the mass of the aluminum times the change in internal energy of the aluminum. And so zero is equal to, the water is mass of 10 kilograms, multiply that by, so now I'm going to substitute in this expression for the change in specific internal energy. So 10 times 4186 times the final temperature, I'll just call it T, that's going to be our equilibrium temperature, minus the initial, which was 5 for the water, plus for the steel, we have a mass of 0.2 kilograms times whatever the specific heat is for the steel, times it's going to arrive at that same equilibrium temperature, but it starts out at 150 degrees. And then plus 0.1 times the specific heat for the aluminum times T, the quantity T minus 20. You could use these, you could convert all these temperatures to Kelvin and do it that way too. You just don't have to because these are all differences. So the difference is the same in Celsius and Kelvin. That's one equation for one unknown. So you can solve that for T. I think this is about 400 or 90. Do you have one for aluminum too? Is 900? Okay, so what, zero is equal to 41,860 T minus, what's 10, what's 5 times 41,860? 209,300. Yes! And then what's that? 9, so 98 T minus 1470. And then 90.2 T minus 1804. Okay, so what do we have here? Can you solve that for me, someone? Okay, 5.37. Yeah, that makes sense because you have a ton of water and not very much of the other stuff. So 5.37 degrees Celsius, just a little warmer than the water starts. Um, okay, what's the entropy produced? All right, so now we have an isolated system. Um, and for an isolated system, the total change in entropy is just going to be the entropy produced. We need to calculate the change in entropy of the system. And we have a formula for incompressible materials. It's that natural log formula. Can someone So for an incompressible material, what's the formula for it's for the specific change in entropy, and it's equal to C times the natural log of something something. C times the natural log of T2 over T1. And so the change in extrinsic entropy is the mass times C times the natural log of T2 over T1. Okay, so the entropy produced is the mass of the water times 4186 times the natural log of the later temperature of the water is 5.37. Oh, we need to do in Kelvin. Um, so 278.37 over 278 plus the mass of the steel, 0.2, times the specific heat of the steel, which is 490, times the natural log of 278.37, that's the later temperature of the steel, divided by the earlier temperature of the steel, which is 273 plus 150, so 423. And then plus the mass of the aluminum times 902 times the natural log of the later temperature, 278.37, divided by 293. So let's just do these one by one. Can people calculate these and just yell out the answers to me? So what we're going to get is, for the individual components of our isolated system, you can go up or down, depending on which way heat is transferring. But when you add them up all together, it can only be positive. Okay. That's joules per Kelvin. 1. Okay. Negative 6.26. And so the total entropy produced is, what do you get when you add those up? Something positive, that's good. Is what? Anyone else do it? 4.62. Okay, so what do you get when you add those up? 10.04 joules per Kelvin. And it's positive, so that's a good sign. For an isolated system, that can never, that's the entropy produced, and entropy produced can never be negative. And you can see how it works, like the things that are giving away heat individually have negative changes in entropy. But when you add them all together for an isolated system, you have to get something positive. And since the universe is an isolated system, this idea is what says that the entropy in the universe just keeps increasing. It gets harder and harder to use the thermal energy that's out there to do useful work, whatever. No, it doesn't mean that. It just what it means. So first of all, 2,000 years is nothing. Things. I mean, the machines still work the same. If you can still get a boiler temperature of 1,000 Kelvin and a condenser temperature of 300 Kelvin, you can still run machines exactly like you could if those were the temperatures a billion years ago or whatever. But what's happening little by little is that as heat keeps going from high temperature things to low temperature things, the universe is very slowly working its way towards having a uniform amount of, uniform temperature everywhere. And once there's a uniform temperature everywhere, I think people call it like thermal death or something, entropy death, something like that. It's like theoretically, at some point, uh, entropy will go all the way up. Everything will be the same temperature. You can't do anything anymore. There's no life or anything. Okay, well, that temperature would be very low, so don't worry, you'll freeze to death first. And also, that's like billions of years after the sun is going to engulf the earth anyways, so it's sort of a theoretical problem. But yeah, it's not that things are less efficient, it's that you can't it's that it gets very slowly harder and harder to separate hot stuff from cold stuff. You can well you can displace it, like um that's right, but it stays in the universe, so you can't get it out of that system. But like inside a refrigerator where you keep the vegetables, you are always decreasing the entropy where the vegetables are because you're pumping heat out of there, and entropy has to do with the amount of heat coming in or out. That's right. So the coils so you're decreasing entropy for the vegetables, but the coils in the back are pumping out heat into the room, and the entropy that uh, the entropy addition to the room is bigger than the entropy loss in the vegetables. Yeah, we'll just have to live in refrigerators. That won't be so bad. Oh, I don't think we're done yet. See, oh, show that the reverse process couldn't happen. Well, the reverse process, um, So for part C, the reverse process would be that all of these three things start at 5.37 degrees Celsius and finish at 5 degrees, 150 degrees, and 20 degrees. Well, this is still an isolated system, so the entropy produced is still just the change in entropy. And the change in entropy for these incompressible materials is the change in entropy for the water, plus change in entropy for the steel, plus change in entropy for the aluminum. So that would be the mass of the water times its specific heat, 4186, times natural log of the later temperature, 5, over the earlier temperature. So this would be 278 over 278.37 plus 0.1 times 490 times natural log of 423 over 278.37 plus 0.2 times 902 times natural log of 293 over 278.37. And all this does is just switch the sign of all of these. So this is going to come out to be negative 55.67. These two will both be positive. Oh, thanks. Wait. Oh, okay, that's good, I think. Oh, no, you're right. You're right. This should be 0.2. This should be 0.1. Okay, and then so negative 41.01, positive this time, 41.01, and then positive 4.62. And so that says that the entropy produced is negative 10.04 joules per Kelvin, and that can't happen. So the second law of thermodynamics says that you couldn't start with these things at the same temperature and have them go off into those other temperatures. Any more questions about that one? Any more homework questions? Okay. Well, there's 3 more topics I want to do, and they're all short. So I'm just going to kind of introduce them, do maybe not even do an example problem for all of them, but and then after that, I'll just spend the rest of the time, like on Thursday, I guess, just going through kind of an outline of what we've covered, try to get you set up for studying for the final. So here are the last 3 topics, brief topics. The first one is entropy balance for control volumes. So just like with the first law of thermodynamics, we first went through stuff where our system is a fixed amount of material, and then we went to the more complicated, mathematically more complicated case where material is moving in or out of the system. We're going to do the same thing now with the entropy balance. And then we'll talk about isentropic processes. And actually, that example that that we talked about last time that I didn't know how to solve in class last time, and that I talked about at the beginning of class today. So the two adiabatic processes in the Carnot cycle, because that was internally reversible, and because there was no heat transfer, there was no change in entropy, right? That was what I said was kind of the key thing I was missing. And so those two adiabatic processes are examples of isentropic processes. And we'll see what we can do in cases where we know we have constant entropy. And then the last thing I'll talk about is one type of power cycle called the Rankine cycle. All right, so the first one is the entropy balance for control volumes. So just as a reminder, remember how we approached the first law, our study of the first law. So first, we dealt with, I guess, I'll start with the differential form of the first law. So it says that the time derivative of the energy is equal to Q dot minus W dot. So this is for a fixed amount of material. Well, that's called a closed system, I guess. And then we expanded on that to, okay, so when we expanded on that for control volumes, we got that the EDT for the control volume was equal to Q dot minus W dot for the control volume plus MI dot times the quantity HI plus VI squared over 2 plus GZ minus ME dot times the quantity HE plus VE squared over 2 plus GZE. And this is a ZI. And so what we had was, we had basically our old equation. These are the three terms from the closed system. And then we added on to that the energy carried into the system or into the closed volume. And we subtracted off the energy carried out of the volume of the control volume. Okay, so it's going to be sort of the same idea with entropy. So with the entropy balance, so first we start with the original expression for the change in entropy, which says the change in entropy is equal to the integral from state 1 to state 2 of dq over t boundary plus sigma. And this process, is this an ideal reversible process, or is this our specific process? Yep, that's right. Our specific process. If this was internally reversible, then you wouldn't have this here, and you would just have the definition of the change in entropy. Let's see. So you could also write this in, we didn't think about it this way, but you could express this in a differential form. That would say ds dt is equal to the integral from 1 to 2 of dq dot over temperature plus sigma dot. And so from that differential form, we're going to get the control volume form. And it says that the rate of change of entropy with respect to time, so ds dt for the control volume, is equal to sum of all the q dots over the temperature at the boundary. What's the difference between writing it this way and writing it the way above? This is just assuming that where heat is crossing the boundary, we have constant temperatures at set of like at a set number of locations with constant temperatures. Okay, so this would be true if the temperature was changing steadily around the boundary or something. You know, this is what we deal with in practice. But those two are really, for any kind of problem that we're doing, those are the same thing. And then we have plus mi dot times the entropy at the inlet, the specific entropy at the inlet, minus me dot times the specific entropy at the exit plus sigma dot inside the control volume. So these two things are the, well, let me do them separately. This is the entropy carried into the control volume. And this is the entropy carried out of the control volume. Okay, who remembers like what kind of processes we dealt with when we were talking about control volumes? So we dealt with, just remember, that was when we talked about those specific categories of devices. We talked about turbines, pumps, compressors, nozzles, that kind of stuff. And so that's the same kind of stuff that we would use this for. Just now we'd be using entropy so we could calculate, different things. But so let's do an example of a turbine. Let's put a box around this. I have all these equations, and this is the only one that's new. So okay, so we have a turbine in steady state. At the inlet, we have steam. With a pressure of 30 bar, a temperature of 400 degrees Celsius, and a speed of 160 meters per second. And then at the exit, we have a saturated vapor with a pressure of atmospheric pressure, 1.01 times 10 to the 5th pascals. A temperature T2 of 100 degrees Celsius, and a speed, let's call that T exit, and a speed at the exit of 100 meters per second. And let's say that for the time interval in question, the heat transfer for the control volume per mass is negative 22.6 kilojoules per kilogram. Does it mean that it's negative? It's, yeah, the turbine is losing heat, heat's escaping into the surroundings. And what are we going to get from steady state? We haven't done this kind of stuff much for a while. Well, first of all, steady state says that since none of these rates are changing in time, we can just think of, so notice that this heat transfer was given as an amount of energy per kilogram. not as a rate of energy per kilogram. But we can just think of like, so say that the time interval that we care about is 54 seconds, you know, we can just use values in kilojoules and just think of that as a rate of negative 22.6 kilojoules, kilojoules per kilogram per 54 seconds. You know what I mean? So we can just do all this with those energies. We can kind of just gloss over the fact that these are finite amount of energies and amounts of energy instead of rates of change. So can use energies rather than energy rates. And then in steady state, properties stay constant over time. And so if we're going to be using, oh, I haven't even asked what the question is yet, but assuming we're going to be using the entropy balance for control volumes, ds dt is going to be equal to 0. And if we use the first law, we also know that dE dt is going to be 0. So dE dt is equal to ds dt is equal to 0. And then the last thing that's helpful is we know that if you look up at this equation, we have, like we used to for the first law, we have separate mi dot and me dot. We know those are the same. We can just call it m dot. And we want to know first what's sigma over m. And since we can do this as energies or as rates of energies, this is also equal to sigma dot over m dot. And then second, what's the work done over m, which is equal to w dot over m dot. Okay, well, we're going to use the control volume equation. So entropy balance control volumes says ds dt is equal to the sum of q dot over the temperature at the boundary plus mi dot times si minus me dot times se plus sigma dot. And steady state tells us that this is 0. It tells us that these two are both just m dot. And it tells us that we can rewrite this as 0 is equal to sigma, the sum of q over tb plus m times si minus m times SE plus sigma. Now, we were given a lot of information at the inlet and the exit. We know the temperature and the pressure. We know the speed. Just with the temperature and pressure alone, we know we can look up specific entropy. So at the inlet, the table says specific entropy at the inlet is 6.9212 kilojoules per kilogram Kelvin. And at the exit, saturated vapor, so we can use the saturation table. So the table says exit is 7.3549 kilojoules per kilogram Kelvin. These are, I don't remember. I don't remember if you do or not. So the second one should be, it says it's a saturated vapor. So you should just be able to use the saturation table. And what we're given is kind of over specified. It tells us what the pressure is at the exit. So if everything that it says is true, then it should tell you in the saturation table that the pressure is at this temperature is exactly what it told us. Okay. All right. So we have that since we're looking for everything per mass, let's divide everything by mass. So we get 0 is equal to 1 over mass times Q over the temperature at the boundary plus SI minus SE plus sigma over M. We are given an amount of heat loss. So we have 1 over M is equal to, there was one bit of information I didn't give you. Let's go back and pretend I did. The surface temperature. So the surface temperature of the turbine is 350 Kelvin. Yeah. Yes, because you can think of that as, that was the thing I said, that we're doing, so for these to be given as energies, we have to be thinking of this over some time interval. That was what I said, like say 54 seconds or a month or something, some time interval. And so we can think of, because this is steady state and those rates aren't changing over time, we can just think of this as, so if the amount of energy being lost as heat is negative 22.6 kilojoules, we can think of that as negative 22.6 kilojoules per 54 seconds, which is a rate, and it all works out the same. So if it's steady state and if those rates aren't changing over time, then you can just totally gloss over that difference. Okay, well, we need that surface temperature. because that's the temperature of the boundary where this heat is being lost. Um, so let's see. This is Q over 350 Kelvin plus the specific entropy at the inlet, so 6.9212, minus the specific entropy at the exit, 7.3549, plus sigma over m. And you can re-express this as 1 over 350 times Q over M. Q over M is what we're given. And so we have 0 is equal to negative 22.6 over 350 plus 6.9212 minus 7.3549 plus sigma over m. And now we can solve for sigma over m. Can someone calculate that? I think everything's in kilojoules. Okay, so sigma over m is 0.498. Mass is positive, so this has to be positive. And this would be in units of kilojoules per kilogram Kelvin. All right, well, so that's the answer to one of these parts. That's the answer to part A. Now we want to calculate the work per mass. So we want W over M. So how are we going to get that? Yes, the first law. And this is still a control volume problem. Anytime we're dealing with turbines or any of these devices, you're going to use this control volume idea. So we're going to use the EDT for the control volume is equal to Q dot minus W dot for the control volume plus MI dot times the quantity HI plus VI squared over 2 plus GZI, and then minus ME dot times the quantity HE plus VE squared over 2 plus GZE. It's steady state, so this goes away. These are both just equal to M dot. And again, we can pass over the rate versus some finite time interval thing. And we get 0 is equal to, I'll write it as Q over M minus W CV over M. We divided out the M's, so plus HI plus VI squared over 2 plus GZI minus HE minus VE squared over 2 minus GZE. And we're trying to find this. Well, Q over M, again, we're given. I guess let's look the stuff up in the table first. So at the inlet, the table says the enthalpy equal to 3230.9 kilojoules per kilogram. And at the exit, saturation table says the enthalpy at the exit is 2676.1 joules per kilogram. We weren't told anything about the height. Let's say this thing is horizontal. That's usually a pretty small term anyways if you're dealing with gases, so let's just get rid of those. We're given speeds at the inlet and exit, so now we can just start filling this stuff in. So 0 is equal to Q over M was one of the things that was given. That's negative 22.6 minus the work over M plus, now we have to be careful. So we have the speed term in here now, which means it's going to be a lot easier for us to use SI units. And so I'm going to put everything in SI units for the equation. So Q over M now is negative 22.6 times 10 to the third. HI is 3230.9 times 10 to the third. VI squared. VI is 160. So 160 squared over 2. Then minus 2676.1 times 10 to the third. Minus, and the speed at the exit is 100 meters per second. So 100 squared over 2. And so W for the control volume over M is equal to negative 22.6 times 10 to the third plus 3230.9 times 10 to the third minus 2676.1 times 10 to the third plus 160 squared over 2 minus 100 squared over 2. So before we calculate that, what do we expect the sign to be here? It's a turbine, so it needs to be generating electricity, so we expect it to be positive. Okay, could someone calculate that? 540 kilojoules per kilogram. Yep. That's right. That's right. So we did this whole thing over whatever that time interval is. Um, so what we have here, if you wanted to express it as a rate, I'm going to keep going with 54 seconds, like some random, you don't know what it is, but it's something. Um, so if we wanted to express this as a rate, um, it would be W dot over M dot is equal to 540 kilojoules per kilogram per 54 seconds. Any questions about that? Okay, let me just introduce isentropic and then we'll do it next time. So isentropic processes. And actually, I didn't say this, but we're only doing this for ideal gases. So we're going to use what we know about ideal gases for this. Okay, what does isentropic mean? Um, it means first, no heat transfer. To or from the system. What's the word for no heat transfer? Adiabatic. And it also requires that the process is internally reversible. So an example of this is, we talk about this example, I guess not for a while, but we talked about like a cylinder and a piston that's insulated, and what happens to the temperature of the gas if you compress it, what happens to the temperature of the gas if you let the gas expand. When you compress it, the temperature goes up. When you let it expand, the temperature goes down. Okay, that is the kind of thing that we would model as an isentropic process. It's an ideal gas inside, and we could use this to figure out what the temperature would be when you compress it, what the temperature would be when you let it expand. Okay. Um, and for an ideal gas, we calculated that the change in specific entropy is equal to S0 at the later temperature minus S0 at the earlier temperature minus R ln of the quantity later pressure over earlier pressure. Isentropic, if the entropy stays the same, that means there's no change in specific entropy. And so we're going to use this equation. 0 is equal to S0 for the later temperature minus S0 for the earlier temperature minus R times natural log of P2 over P1. And you could just do your problems from this, but it turns out that it gets a little messy when you're solving for, we're trying to come up with a we're trying to derive an expression for P2 over P1, how those pressures relate to each other. And so we're going to introduce a couple of new uh, properties that you can look up in the table that just make it so you don't have to do as much math. Okay, so this is the starting point for next time, for Thursday. Any other questions? Yes. No, not because isentropic also means a reversible process, an internally reversible process. So you could have, you could have a very well insulated 1950 John Deere tractor that's very inefficient but still adiabatic. Mm-hmm. Isothermal and isentropic. For a Carnot cycle, for any reversible cycle, they're synonyms. And the Carnot cycle is reversible, is internally reversible. So, but if you have a cycle with irreversibilities, even if it's adiabatic, it's not isentropic. Any other questions? Okay, that's it.